Now we're going to talk about oscillations. And we dealt with oscillations when we were, well, you've seen the word oscillations before with waves. Just think of an oscillation as a cycle. I'm going to give you a more formal definition of it in a minute and then how it applies to simple harmonic motion. Just as a refresher, the equilibrium position is where an object where an object is at rest. The important thing here that you need to focus on is that there is no net force acting on it when the object is at rest. We have a new definition here called a restoring force, and that's a force that acts to restore equilibrium. So when you move an object away from its equilibrium position, the restoring force is what's going to try and bring it back to the equilibrium. The farther away you are, the greater the force you're going to have. So when you're farthest away from equilibrium, that's going to be your greatest restoring force. There is no restoring force once you're at equilibrium. An oscillation is a repetitive motion if an object is moving back and forth through its equilibrium position, characterized by a period and a frequency. So just to remind you, period is the time it takes for one oscillation. Frequency would be the number of oscillations in a second. Simple harmonic motion is characterized by an object moving towards its equilibrium position due to a restoring force. When we're dealing with simple harmonic motion, you're going to see this kind of motion. So sines and cosine graphs, or in other words, they're going to look like transverse waves. So simple harmonic motion is actually a wave motion. However, you're not dealing with a wave itself. So you have a period and a frequency, you're going to have an amplitude, but you don't necessarily have to worry about wavelength or anything like that. The first type of oscillator we're going to look at is a mass spring system. So a mass spring oscillator is simply a mass attached to a spring, either horizontally or vertically. The spring is what's going to exert a restoring force back toward the equilibrium, so therefore spring force is going to be your net force. It's directed opposite the direction of displacement, and from a really long time ago, spring force equals K delta X. So this can be positive or negative depending on the direction of the displacement. You might also see this as just negative K X, and that's if they're treating any displacement as being positive. So you've seen this equation before. It was a really long time ago, but here it is coming back. We're going to deal with ideal springs because that makes life easier, so you don't have to worry about the spring constant. And in case you forgot what all of these were, K is your spring constant. X would be the distance from equilibrium. So you can see how where you're getting farther away from the equilibrium, your X is going to increase. Force is directly related to that distance, so that's why the farthest from equilibrium, the largest your spring force will be. Okay, and this is for a horizontal spring. So all this is going to look like. So horizontal mass spring system, you're going to have a spring connected to a wall. You're going to have a mass connected to the spring. If this is equilibrium position, this is where the object would be at rest. It could go out here, so this would be your delta X, or it could also go back. So this could also be delta X. And your maximum distance from your equilibrium, this delta X, is referred to as the amplitude. So your amplitude is the maximum distance it gets away from the equilibrium. So you'll see me interchangeably using delta X, and you might also see a capital A for amplitude. So this is a horizontal spring. Let's now look at a vertical spring. vertical springs are going to be hanging vertically and they're not going to be on a surface. So when you have a vertical spring, it'll be hanging from the ceiling, and then the oscillations, so this will be the equilibrium position. It'll go up and down, past the equilibrium. So it can go down, and it can also go, up. And in this case, that distance, this is not drawn to scale, and this distance, so the distance from the equilibrium position is again your amplitude. So amplitude or your delta x. So for vertical springs, unlike horizontal springs, they're going to have two forces acting in the direction of the restoring force. However, weight does not affect the restoring force. The only thing the weight of the mass itself does is tell you where the equilibrium position is. So you have a spring, you put a mass on it, it's going to stretch the spring. What the weight does is determine how much it stretches to get to that equilibrium position where the mass is at rest. You then cause the spring to oscillate by letting it go down or up, so you either pull it up or you pull it down, and it'll go up, down, up, down, up, down. The restoring force that brings the spring back to the equilibrium position is not the weight, it is still the spring force. So it's still going to be spring force equals K, and instead of X, Y, but it's going to work the same exact way as X. So it's just the distance that the mass gets away from the equilibrium. And that would technically be negative if it's the opposite direction of the displacement. So for both horizontal and vertical springs, the restoring force is the spring force, and it's just Hooke's law. We're using ideal spring, so we don't have to worry about spring constant. And when you're dealing with vertical springs, the fact that these do have a weight only determines where the equilibrium is. It does not factor into the restoring force. The only other thing we want to look at right now for these mass spring oscillators is the period. Period depends on the mass and the spring constant, and we're not going to derive it. I'll just give you this equation. Period equals 2 pi square root m over k. So obviously 2 pi is a constant, m is the mass, and k is the spring constant. And you do have this formula on your formula sheet. So looking at this equation and the relationship, if you increase the mass hanging on the bottom of the spring, you're going to increase the period. It's not a direct relationship, it's a square root relationship. So doubling the mass isn't necessarily going to double the period. If you make the mass 4 times what it was, then your period will be twice as much. The period is inversely related to the spring constant. So a higher spring constant means a lower period. Think of it this way. Spring constant is how hard it is, or how stiff a spring is. The stiffer the spring, the faster it's going to respond, so your period's going to be less. The greater your mass, the longer it's going to take to stretch to go all the way down and come all the way back up, so that would increase the period. So you do need to know what the period depends on. You do need to know how both the mass and the spring constant affect the period, and this is the only equation that really tells you how all of that works. Because period and frequency are inverses, frequency would equal 1 over 2 pi square root of k over m. So this is not given to you, but it is expected that you recognize that period and frequency are inverses. Okay, I'm going to do one example. It tells us that a spring has an unstretched length of 10 centimeters. A 25-gram mass is hung from the spring, stretching it to a length of 15 centimeters. If the mass is pulled down and released so that it oscillates, what will be the frequency of the oscillation? You definitely want to draw a diagram here. So we have a spring unstretched with a mass on it, and the unstretched length is 0.1 meters. And then, keep doing that. the mass is placed on the spring. I drew this wrong. It's the length of the spring, stretching this to 0.15 meters. If we list what we know, the stretch of the spring, so delta x, equals 0.05 meters. It tells us that the mass hanging from the spring is 25 grams, so that's 0.025 kilograms. And that's all we know. And we're looking for the frequency of the oscillation. So the first thing I really want to do is draw a force diagram. When the mass is here, so actually there should not even be a mass here. This is just an unstretched spring, so that's not there. Nothing there. Okay, so when the mass is on the spring, it's not moving, it's in equilibrium, meaning it's at rest. So if we draw a force diagram for that situation, we have the spring force pulling up, and we have an equal weight going down. So that means that your spring force is equal to the weight. So your spring force equals mg. So this equals 0.025 kilograms times 9.8 newtons per kilogram. So our spring force equals 0.245 newtons. We also know that spring force equals K delta X. We know delta X, we need to figure out K. So spring force over delta X equals the spring constant, 0.245 newtons, divided by 0.05 meters equals K. And this comes out to 4.9, and if you recall from when we did energy, the units for spring constant are newtons per meter. We're looking for the frequency of oscillation. Frequency equals 1 over 2 pi times the square root of k over m. So this equals 1 over 2 pi times the square root of 4.9 newtons per meter over 0.025 kilograms. And this comes out to 2.22, keeps on going, hertz. So the frequency of oscillation is about 2.2 hertz. If you were looking for the period, you would just take the inverse of that. So 1 over 2.2, period's about 0.448 seconds. Okay, so conceptually, what you really need to know about the mass spring oscillators, what affects the period or frequency, how those things affect them, and what the restoring force is. So anytime you're dealing with mass spring oscillators, restoring force is the spring force, and we're using Hooke's law for an ideal spring.